If it weren't for dreams, we'd never have built India's leading private steel enterprise, or wouldn't have expanded while the world was witnessing a downturn. If it weren't for dreams, we wouldn't have created new gateways into India, or would have drawn blueprints for one of India's largest power companies. If it weren't for dreams, we wouldn't have schooled tens of thousands of children, or developed a self-sustained township. If it weren't for dreams, we wouldn't have seen doors where others saw walls. If it weren't for dreams, we wouldn't have built an $11 billion enterprise. JSW, bringing alive a billion dreams.
Carter Emmart is a kind of childhood fantasy. He's an astronomer that's used complex computer and digital technology to create a 3D atlas of the known universe. And this afternoon, his presentation is going to take us millions and billions of years back into time, because as we all know, the light of the stars that we see is traveling to us from a time that is already over. So ladies and gentlemen, please welcome Carter Emmart.
Thank you. I want to thank the THiNK staff for inviting me here at a time when I wasn't sure I was going to be able to get away from New York finishing a production. It is a great, great honor to share this stage with so many here. And I want to thank as well the staff in the back who have made the visuals possible for today, KK and Rahini, for helping me out. The visuals that I want to show, if we could bring the lights down a bit. If we could, thank you. Because today I'd like to share with you a little bit of what I do in New York with a little bit of music from U. Srinivas. This is how I invite my friends into the planetarium after hours. And I roll out a carpet with pillows, and we can lay down in the middle of the venerable Hayden Planetarium, which was rebuilt in 2000. The previous picture was 1935 when it was built, and that's how it looked when I started going there at the age 10, when my mom used to drive me in every week from New Jersey to take classes there. And we rebuilt basically to go from the sky into what we know of space, because of what technology has given us. And so what I'd like to do now is take us on a ride on out to space. I'm going to grab my laser. I'm a child of Apollo. I was 8 years old when we landed on the moon, and really this realization of going out into space, going beyond the satellites, the thousands of satellites which we see here, really was a realization when we got out there looking back for us at our home planet. What you're seeing here in this digital universe that you're seeing on either side here is a compilation of data, and we visualize that data put together into one large data set we call the digital universe. And as we go out, we chart the exact paths of the planets, and we can come close to them and look at them, but also on out into the stars. Because what we're dealing with is a map of the universe which really has been put together by humanity over generations. It's not anything that any one person could do. It's something that culture has done, global culture in science. And so as we go out, here we see the paths of, this is Voyager 1, Voyager 2, and also Pioneers 10 and 11. These four craft have left the solar system. They're being joined now by the New Horizons mission, which in a year and a half will pass the planet Pluto. As we go out, we see our sun shrinking away and joined by the other nearby stars. And as we can see, they're labeled here, but the backdrop of the Milky Way is really this larger family of stars that we live in and from which we come from. Right here, we're showing the positions of stars that we now know have planets. When this production was made, I did this production in Sweden, we had about 300 exoplanets known. They're now about just under 1,000. And beyond that, the Kepler mission is also looking at a particular part of sky, and there's several thousand candidates that are being monitored. As we move farther out, we see the line, the stars connecting the zodiacal, the lines that indicate the zodiacal constellations. As we pull out, that sphere represents how far radio waves have traveled since the birth of radio, essentially strong enough to get beyond the ionosphere around the time of World War II, quickly lost against the Milky Way galaxy. The galaxy itself comprises, by extrapolation, we know of about 100,000 stars around us, but beyond that, we have the extrapolation of stars that we know, several 100 billion stars. And with the rate that we're finding planets, perhaps 1 trillion or more planets in our one galaxy. Every point you see now beyond are charted galaxies. Every position, there's the Andromeda galaxy closest to us. It's about 2.5 million light years away. So we see it at the time the humans weren't even walking the planet yet. Louise Leakey yesterday spoke about the origins of us, really several 100,000 years ago. The galaxy itself is about 100,000 light years across. It would take 100,000 years for light to cross it. Every position here is a known galaxy that's been charted. They're color-coded for association, so we can see reds, actually quite nice here, reds showing the clusters of galaxies. Right here is the Virgo cluster, about 1,000 galaxies, and about 60 million light years away. As we go out, we have more and more surveys that are coming in. When we started this job of plotting the three-dimensional universe around us in the late 90s, we had about 3,000 galaxies. We now have, this is the Sloan Digital Sky Survey that we see in aqua, and then in yellow, this is a 2-degree field survey. Also, as almost like a haze of galaxies, this is the 2-micron all-sky survey. Altogether, this is about 2 million galaxies that have been charted really within the last decade. It's a tremendous testament to the science that we're now able to do. You might notice these blank areas. This is areas we've yet to chart, basically because our Milky Way blocks that view. 2 million galaxies is a lot of galaxies. Multiply that by about 10,000, and you come close to the true census of galaxies that are out there. If we extrapolate from what we can from what the Hubble telescope can see, just looking in a patch of sky and counting the galaxies in a very small part of sky. Beyond all this is the cosmic microwave background. And so what we're seeing is this sort of afterglow of the Big Bang. We're actually seeing light that left when the universe was fresh as a baby, was really just about several 100,000 years old, and was cooling off. And so what we see is slight temperature variations, and those slight temperature variations over the evolution of the universe lead to essentially the distribution of matter, the lumpiness that we see. We're going to pull out once again, actually, from this view of a galaxy with a broader view. The circle that you see represents a sort of fisheye view that we project into the dome at the planetarium in New York. And so now we're pulling out once again, but this gives you a better view of this horizon that surrounds us uniquely in our position. We are in the center of what we can see of the universe, but this is just our visible sphere. Stepping outside it, we can see, just choose another position, another place, another galaxy. They can see beyond our horizon, and we can see beyond theirs. We don't know how big the universe is. It may well be infinite. But we're governed by essentially our position and light traveling to us. We don't know how big the universe is. The universe could well be infinite. And so what you see here are just multiples of that. If you look at the way galaxies and galaxy clusters behave, we can see that there's not enough mass accountable from what we can actually observe of galaxies. And so we know in a simulation like this, using dark matter, in fact, everything you're seeing here is dark matter in this simulation. This is from Tom Abel from Stanford and visualized by his visualizer, Ralph Kaler. But we directed this from New York. We chose a color scheme against a background that's gray, essentially, to show the dark matter as dark. And so what we're seeing is the simulation of the universe starting off from the very early homogeneous stage where it was dark, and what's happening is gravity, those slight temperature variations lead to slight mass differences that start to pull in and cluster the universe. And these simulations don't work right unless we have about 6 times the amount of matter that we actually see and account for stars and galaxies and so on. We know that we're outweighed in the universe by dark matter by a factor of about 6. If we looked at our galaxy over 100 million years, it would look like this. In fact, this is a downsampling of how many stars are actually exploding. The heavy massive stars, which cause the galaxy to glow blue out in the spiral arms, their stars are being born, actually live for a very short amount of time and then they blow up. And so what they're doing is these stars are essentially exploding, and what they leave behind is the stuff that makes us up. The iron in your blood, all the heavier elements are forged. If we look now at an accounting of the universe, dark energy is something that we're seeing here. We see these are time shells moving farther out. This is farther back in the past, and this is closer to now. And we can actually see, using these supernovae, we can get the distances to the galaxies as they're expanding away, and we can judge that the universe used to be expanding slower than it is today. This dark energy dominates the universe, makes up about 70% of the universe. Then there's about 25% of it that's dark matter, and we are only less than 5%, everything that we can see. So all these galaxies are essentially like the glowing froth on top of an ocean that we only see the white caps of, and that are the galaxies that make us up. This is the Milky Way galaxy sailing home. These are the Magellanic Clouds. We're crossing the disk of the galaxy and coming back home. Out here amongst the galaxies, everything that's been charted, that we start to look at the galaxy as if it's home. We come in this myriad of stars, hundreds of billions of stars, perhaps 1 trillion planets. One of these stars is us. This is the Hyades cluster. It's about 150 light years away from us, and we're now flying back through the radiosphere. So that sphere represents the sphere of emanating radio waves that are reaching out into space at the speed of light, but that's currently where it's set. We're coming in here about, let's say, 1 light year away. Now we're 1/10 of a light year, 100th, 1,000th of a light year, essentially, comprises our solar system. So the nearest star, Alpha Centauri, is about 4,000 solar systems away, very far. And we finally come up to this little third planet from the sun, this tiny little place that we are. In the center, I'd like to point out our thin habitation zone. Essentially, we are creatures that live within this atmosphere. We live at the edge of water. We need water. But we don't live on mountaintops. As people, as complex organisms, we essentially live in this zone that's immersed in this atmosphere that's held onto by our planet. What are we doing to our planet? Here we see China. This is actually October 3rd through 9th. We see right here the East China Sea. This is Korea that's just set, and we're seeing essentially the pollution of rapid industrialization. This is Mount Sarychev, which is in the Kuril Islands between Kamchatka and Hokkaido. and that was filmed from the space station. Volcanoes essentially rejuvenate our atmosphere, and so we're seeing that here, that we need that atmosphere rejuvenated. The Himalayas are active Earth because that we still have an inventory of a warm interior that causes the geology to work this way, is that these are still being pushed up, and it traps the Indian monsoon, the rains that come in and create the snows in the Himalayas. And that's the water for this part of the world, flowing north into China, flowing south into the Ganges and the Brahmaputra. Here, this is Assam region, and the convergence right here of the Brahmaputra and the Ganges. And this is the Valley of Lhasa down here. Over here, Google has put together an animation looking at Landsat images over 30 years of data. And so they can create these animations of essentially what's happening to our environment. These are the tar sands in Canada. We just saw the Rondônia region of the western Brazilian rainforest. And so we can see these changes that are occurring across our planet. We are rapidly, very rapidly, consuming the surface of this planet, altering it. Almost looking like a video game here, but in Wyoming we see the coal mining that's occurring. With this ability, with planetariums, to really take this and bring this to people, is that we're looking at ways in which that we can share this experience. And we've been able to do this by linking up domes. And so that we have this notion of dome casting, that as I drive the digital database, we can drive that to other major planetariums. The World Views Network is a National Oceanic and Atmospheric Administration grant that we got basically to run Chicago, Denver, San Francisco, and New York, and we can cooperate. We're creating programs on eco-literacy, and here is a program going on in the Denver Planetarium, as you could see it, as if you're immersed in space. So a world network of planetariums is essentially what we're working toward, in a sense, to reach out to the world and bring this together. In 2002, I visited Arthur C. Clarke in Colombo, Sri Lanka, and it really opened my eyes to traveling and being out in the world. And from that visit, essentially, I started to think, how could we really bring this out? We have the Earth, in a sense, having an identity crisis. So many problems were rapidly evolving, coming together. But in a sense, that view from space unites us, especially the higher out we go. In 2007, I visited Cambodia for the first time. And there at Siem Reap in the Makara High School, because Angkor Wat is essentially a Hindu cosmogony, and I did not know this when I went there, was that I was touched by that, in a sense. I was touched by the people and everybody I met. So I came back about 4 months later with a computer and looking for a high school in which I could share our model of the universe with theirs. And so at this high school in Cambodia, we actually can do this. I can control their screens, and they can actually control the Hayden Planetarium from their high school. Over here, continuing on with the time lapse that we see from Google, we can see Las Vegas. It's the fastest growing city in the United States. And also now we can see the time lapse as well in Dubai, and the rapid development there that's been occurring, again, within about 30 years. This is a map of the world that everybody gets an island to live on, if you have enough money. This is the physics teacher, Pirak, and myself in the school in Siem Reap, where I go every year and teach. The jewelry I'm wearing is essentially from the young kids that sell the jewelry out by the temples, and it's my pledge insofar as coming back to them every year. Here we actually see Pirac while he was controlling, and the students controlling the Hayden Planetarium from their high school. Flying over the Earth at night, we're just passing the Nile. This is, we see Turkey and the Black Sea, the Caucasus Mountains. And right here we can see, this is the lit up border between Pakistan and India. We can see thunderstorms over the south of India and Sri Lanka, and the moon's glint. This is the air glow layer. It's a sulfur dioxide that we see in the sulfur emission. These are the aurora borealis that we see actually, and the aurora australis over the southern portion of the world, filmed by the space station. The space station actually flies through these veils of the aurora, especially during periods of high solar activity like we have right now. In Ghana, there's a planetarium that was pretty much home built, but they got a donation for a projector so that we can actually work with them. And although I've never been there, for their opening ceremony, I gave for about 3 hours tours of the universe to their planetarium from ours. And so this future that we had considered that must be somehow in space, this notion that perhaps we do have a future. The lunar base would be below. This is the crater Tycho, so this is Clavius, and down below, just off screen, is the South Pole. However, I bring us close to the moon right now so that we can actually really see the difference of the moon to the Earth. The Earth really is our unique environment. The Earth is large enough to hold a thick atmosphere for us to breathe. The moon, being a quarter the size of Earth, does not have enough mass to hold on to an atmosphere at all. This crater here is Tycho. It's 80 kilometers across. Its central peak is about 2,000 meters tall. And this is one of the youngest craters on the moon. It was formed when an asteroid hit the moon about 110 million years ago. We know that because we were able to date it with deposits thrown out of this crater, even though about 1,000 miles away, to the landing site of Apollo 17, our last mission to the moon. Also, inflatable planetariums. We're able to deploy these. NASA has one, and President Obama had a star party in 2009. And so we went there with the NASA Goddard Geodome, they call it. But it's really this idea of calling it a geodome is this focus as we go out to really look back and appreciate this planet from which we come. Coming closer on the moon, we can see details here from the narrow camera on the Lunar Reconnaissance Orbiter that gets down to less than a meter resolution. So if there were cars on the moon, we could see them. In fact, we do see the cars that we left in the three of the last missions to the moon when we left cars there, Apollos 15, 16, and 17. But this is the central peak of Tycho. When you view this in the dome, it's as if you're sort of flying over it. It's as if you're right there. But again, the moon is a harsh environment. We've been there, but really going there was really about sort of looking back and seeing home. It wasn't what we went for, but we realized that after we went. Mars, the next planet out, is the most Earth-like planet in the solar system. It has craters like the moon. It's an ancient surface, billions of years old, but we can also see it was altered by flowing water in the past. And so that we see this. This is Ares Vallis, and you can see the atmosphere on the moon. One project that we're working with right now, I have my high school students working on it, is also working with the Lower East Side Girls Club. This is in a former ghetto of the Lower East Side of Manhattan. And that there's a lot of data from these missions, especially to Mars, where we can turn that around and essentially utilize that. And my high school student, Kiara, right here, is actually teaching younger girls down to the 8th grade level to actually use the NASA software to take the results from the Mars rovers there that are examining and have been examining for 10 years. These are the two rovers, Spirit and Opportunity, that have been there for 10 years, looking at very close-up portions of Mars. The digital universe is an amalgam of all this. It's a synthesis of all this data so that we can fly through this. This information that we're looking at here is in the central Valles Marineris, and we can see the layered terrain and so forth. This is from the Mars context camera on the Mars Reconnaissance Orbiter. This is Kiara teaching, the teachers actually, the process to turn the microscopic imager results into 3D models. And this is Dave Pentecost and his wife Lynn. They started the Girls Club. Here we actually see the rover deploying its tool in a visualization. And these are the results of this data that are online and available. But the scientists have not had enough time to go through and actually process it all. And so our students are actually augmenting what they're doing, and so that these little models that can be created become part of the digital universe. Flying over here, Candor Chasma, Ophir Chasma, we're seeing more layered terrain of Mars. And this was flown live in the dome and recorded. And so the central camera I'm just bringing with to share with you here of what Mars really looks like. And so we get down to details here that are truly extraordinary. Earth really is our paradise. If you look at Mars, it's like there are no trees. The air is very thin. It's equivalent to about 100,000 feet on Earth. It's extremely cold. But Mars is fascinating. This is where the rovers landed, and this is the type of thing we're working with. This is the rover data. When it looks out, it takes stereo images, and these almost like lily pads around the rovers are spots where the rover looks out and we can see the rocks. Using levels of details, we come closer, we can see those rocks in greater and greater detail. And then we can take the microscopic imager results of these models that are being produced, again, by high school students and elementary school students, to put that together into this global map of Mars. Here's an example. This is only 3 centimeters across, but this is one of the results my students have come up with using the NASA software. And from this, we can actually 3D print this. We have brought Mars with this data to Earth. Earth is our home. We may go to Mars, we may go beyond, but really, it's our planet. This is vital that we figure out how to live together on it. The perspective of space is broadening, is amazing, is truly extraordinary. But looking at this, essentially, we're now bringing this data here. We have a mountain of data to process here. It takes us there. We are there. Thank you very much.